Hello, this is section 8.3 t-test for a mean. So when we actually use a mean, but this time as a sigma is unknown, we're using the t-test. So you gotta remember, test the mean when sigma is unknown using the t-test. Alright, so most often than not, the standard deviation of the population is unknown. So the z-test is not typically used for the test hypothesis involving mean. So t-test is used instead. So the distribution of the variables should be approximately normal. So the property of the t-distribution is similar to the standard normal distribution. So you got the bell shape, symmetric, and the mean and median mode as equal to the zero. Locate the center of the distribution, and the curve approaches but never touches the x-axis. And property of the t-distribution that differ from the standard normal distribution. So standard deviation is greater than 1. And then t-distribution is a family of the curve based on the degree of freedom, which is related to the sample size. And then as the sample size increases and t-distribution approaches the standard normal distribution. So definition of the t-test. So t-test is a statistical test for the mean of the population. Is used the population normally and approximately normally distributed, and the population standard deviation is unknown. So that's actually difference. Okay, so t equal to x bar minus mu over s. We use the s actually the sample standard deviation with the degree of the freedom. All right, so we're going to use the table F to find the critical values for the t-test. Remember, for the degree of the freedom larger than 30, round down to the nearest table value for the consecutive approaches. As the degrees of the freedom get larger, the critical value for the t-test approaches the z values. So assumption for the t-test for the mean when the sigma is unknown. Number one sample is a random sample. Either n is greater or equal to 3, or the population normally distributed when n is less than 30. So that's what we need to state that. And then procedure for the t-test by the traditional method. And step 1, we are state null and alternative hypothesis and identify the claim and find the critical values, and then compute the t-test, and then we decide to reject it or not reject it, and then summarize the result. Okay, how about the p-value, which is that's a traditional, right? So p-value, state the null and the alternative hypothesis, of course, and compute the t-test, and then p-value rejected, do not reject it by the p-value with the alpha, and then summarize the result. Okay, so let's do the problem. So example 1. Find the critical t-value for the alpha equal to 0.05 with the degree of freedom of the degree of freedom is already 16. Alright, so let's look at the table we have here. So when you look at the table, alright, so this is the degree of the 16, so we have to look at here. And then the alpha is 0.05. So alpha is a 0.05, which is right here, 0.05. It's a one tail this time. So the intersection is 1.746. So answers is the critical value is gonna be the 1.746, which is a right tail. So one tail, okay? And then B, find the critical value, t-value for alpha equal to 0.01, and then degree of freedom is 24 for the left tail test, okay? So let's do again. So with the formula and table, now this times we have to use the degree of freedom of the 24. Sorry, we have to use degree of 24. And then I have to find the 0.01 for the one tail, okay? And then I see the number as a critical value was 2.492. But since this is the left tail, and then I can say this the critical value is going to be the negative and 2.492. All right, C. Find the critical values for the alpha equal to 0.01, but this is a two-tail, but in two-tail, we are using the alpha over 2, which is 0.10 over 2, which is 0.05, or you can just use a two-tail from there too. So let's see. So formulas, okay, so clear the table. So degree of freedom is 18. So here's 18. And then we have to find the 0.10 as a two-tail. So if you do this, actually you can use this one or this one, okay? If you alpha divided by 2, you can use that one. And you can use this one. But this is two tails already here, so you don't really need to divide it. And then we are looking for the intersections. Okay, so I see the 1.734, okay? So so we're gonna get the critical value this time, which is one is a negative 1.734, and also 1.734 on the right. All right, next page. Now let's test them out. So example 2, hospital infections. A medical investigation claims that the average number of infection per week at a hospital in southwestern Pennsylvania is 16.3. A random sample of the 10 weeks had a mean number of the 17.7 infections. The sample standard deviation is 1.8. Is there enough evidence to reject the investigation claim at alpha equal to 0.05? Assume the variable normally distributed. So in here, so h of 0, which is the mean was 16.3. And then alternative hypothesis, which is a mu is not, which is a different this time. So it's not the greater or less than, so it's different from the 16.3, which they just say about the 17.7. So in the the value at alpha equal to 0.05, but this is a two-tail because of not equal to. We have to find the alpha over 2, which is a 0.05 over 2, which is 0.025, or you can just use a two-tail for the 0.05. Okay, and then n equal to 10 weeks, right? So they talk about weeks, right? So now we have to find the critical values this time. So which is going to be plus minus, okay? So I'm using the degree of freedom from is 10 minus 1. So which is a 9 in here, okay? So let's go to the table. So it's gonna be the degree of freedom is 9, and then the 0.025, or we can use this one for the alpha for two-tail, okay? So I'm going to do the find the intersection, which is 2.262, okay? All right, so it's going to be in the plus minus of 2.262. Now we have to find the test statistic, but okay, before that, actually, we can kind of use the curve to see where that is, okay? So this time, the one is a negative 2.262, which is this side, and the other one is 2.262 is this side, okay? Now we need to find the test statistic, which is a t-value. The formula is going to be x bar minus mu over s over square root of n, which is 17.7 subtract 16.3 over 1.8 over square root of 10, which come out as 2.460. So now I'm going to found the place of the 2.460, which is about here. 2.460, right? So the test statistic is falls into the critical region. So because of that, we need to reject the null hypothesis, which is different because 2.460 is greater than 2.262. So we can say there is enough evidence to reject the claim, which was a claim was the null hypothesis actually this time, and that the average number of infection is 16.3, which is different from the 6.3. All right, next page. Aspirin consumption. All right, medical researcher found that the people who take the aspirin take on average 8.6 tablets a week. A medical doctor wanted to see if he could reduce the number of the aspirin tablet per person consumes if the subjects practice the yoga twice a week. A random sample of the 12 people who take the aspirin were taught yoga, and after 12 weeks period of the doctor found that they took the following number of the tablet for 1 week. So 7, 4, 6, 8, like that, okay? So, I need to actually add something that I'm missing from that. Yes, it must be that we test the claim at alpha equal to 0.10 and also assume the variable is normally distributed. Alright, so let's find the x bar, which is the mean of the sample, which is going to be added up and divided by 6.8. And then also standard deviation, use the formula. We got the 2.37. And then degree of freedom, which is there's 12 people, so it makes it 11. So h sub 0, which is mu equal to 8.6. And then this time, h of 1, mu is less than 8.6, which is it is actually the left tail. So critical value at alpha equal to 0.10, where the degree of freedom is 11. And then we can find the... Alright, let's look at the table. Okay. So degree of freedom is going to be 11 from here. And then it's a left tail, so 0.10, which is right here. So, okay, this is the number that you can find it. All right, so 1.363. So in here, the critical value is going to be the negative, but it's going to be 1.363. So if you are making a normal curve, and then 0 is in the middle, of course, and then here's a negative 1.63, and then this is the critical region. So when you find the test statistic falls into the critical region, and then we can reject it, otherwise we do not reject it, okay? So now we have to find the test statistic, which is a t equal to x bar minus mu over s over square root of n, which is x bar is 6.8, subtract 8.6, and then s is 2.37, and then divide by n, which is a 12, then I got negative 2.63. Now we need to see where this goes to. So it's a less than here, right? Isn't it? It's a negative 2.63. So the test statistic falls in the critical region. So now you need to conclude that we have to reject the null hypothesis, which means there is enough evidence to support the claim that practicing yoga reduce the weekly aspirin intake. Okay. Alrighty. Okay, so let's look at the next problem. Okay. Now we try to use a p-value this time. So use the table F to find the p-value. So I have actually the table in here to use. Okay. So t equal to 2.321 and n equal to 15. So first of all, we need to find the degree of freedom, which is n minus 1, which is the 14. So from the 14, okay, which is the 14 is right here. Oh, that's too big. Sorry about that. So for the 14, I'm looking at these rows. And then I'm looking for the number closer to 2.321, okay, because I'm looking at the number of the 2.321, okay. So 2.321 is between the 2.145 and 2.624. So I can say 2.321 is between 2.624 between 2.145. Now we are looking for p-value, which is gonna be the percent. Okay, so if I looking up for the right tail, which is a one tail, so if you go up, you'll see that it's gonna be 0.01 and 0.025. So I can say this one is between 0.01 and 0.025. And then we compare to the alpha, which is a given. All right, next one. T equal to negative 1.415, n equal to 24. So degree of freedom is going to be 23 with a two tail. Okay, so let me actually erase it. All right, so next one. Now, we have to use, there's no negative, so we just consider this is actually the positive, okay? So I'm looking at from the degree of freedom 23, which is right here, okay? And then I'm looking for the number that will be between the two numbers that can be included 1.415. So I see these two numbers. Okay, I see these two numbers. So I know that 1.415 is between 1.714 and then 1.319. But this is actually the negative. So if you multiply by negative both sides, it becomes, you know what? I think I should have used the percentage first. Okay, so sorry about that. So let me actually erase this. I'm sorry. Okay, so let me erase this. Okay, so we are looking for the p-value, right? Which is 1.74 with a two tail is going to be 0.10, and then it's going to be 0.20. But we are looking for actually the negative, right? Right? So we have to get negative. When you multiply by negative, you gotta actually the reverse. It's the inequality. So inequality becomes this way. So you'll see, yeah, of course, and that's the right way of the direction too. Okay. Also the left tail. Okay, so t equal to negative this time, but n equal to 17. So degree of freedom for this one is 16. So I want to erase this. So 16 is right here. Okay. Then I'm looking for this number, which is absolute value of that. And then as a 1.862, it's going to be 1.862 is between the 2.120 and this two number I'm talking about, okay? 1.746. But this is a negative, so yeah, you can put a negative here. So negative 1.862, which means you gotta multiply both sides, becomes negative 2.120, negative 1.746, right? So now this is a p-value, and then corresponding to the alpha with the left tail. So if you go to up to here, so this is a number, go up to here, and this is the numbers. So the alpha is going to be you got 0.025 and then 0.05, okay? Then the alpha is going to be the greater than the p-value, and then we rejected our hypothesis. All right, okay, go to the test hypothesis. So that's the problem. So jogger's oxygen uptake. The physician claims that the jogger's maximal volume oxygen uptake is greater than the average of all others. A random sample of the 15 jogger has a mean of 40.6 milliliter per kilogram and a standard deviation of 6 milliliter per kilogram. If the average of all others is 36.7 milliliter per kilogram, is there enough evidence to support the physicians at alpha equal to 0.05? Assume the variable is normally distributed. Okay, so h of 1, which is mu equal to 36.7, and null hypothesis, h of 0, what am I doing? H of 1 is mu is now the greater than 36.7, which is this is a right tail. All right, so, and then the degree of freedom, which is 14 because there are 15 joggers. Okay, so we need to find the test statistic, which is a t equal to the x bar minus mu over s over square root of n. So x bar was 40.6 minus 36.7 over s equal to 6 over 15 joggers and become 2.517. So I have to use the 14 and then 2.57, right? So 2.517 is in between which two numbers, okay? So let's go back to the previous problem as a table, okay? So hopefully we can find it there. Okay, so clear the page for that. Oh, sorry. Did I clear the whole pages? Okay, sorry, but you had it already, right? Okay, so on this case, and then I'm looking for the degree of freedom of the 14. And then the number that the test statistic is a 2.517. So 2.517 is between these two numbers, right? Okay. This number and this number, right? Okay, so I need to remember that. So in between the 2.624 and 2.145. So it's a right tail, so we don't have to use any negative this time. That's a good thing. And then find the alpha to relate to. And then you need to go up to the one tail, which is this number. One tail is going to be this number. Okay, so go to the here. So sorry about that. So 0.025. And then it's going to be 0.01. Let me see. 0.1 is a bigger. What am I talking about here? It's not right. So I need to put the 0.01 and 0.0. hold on a second. That's not right. 0.025. So the one tail for the 14, that's related to the 0.01 and 0. We gotta put it other ways, right? Yeah. This time doesn't really match this time. So 0. Yeah, we have to make that as an inequality correct, okay? So we have to say that as, okay, erase that. So this is a match of the 0.025 and 0.01. Okay, now what you do is, this is actually the range of the p-value, okay? So p-value is it less than alpha? So alpha was 0.05, so but two numbers, both of the number we have here, right, is less than 0.05. So we just need to write the null hypothesis. That means greater. So that means there is enough evidence to support the claim that the joggers' maximal volume oxygen uptake is greater than average person. Okay, all right. So that's for the 8.3. All right, thank you for listening.